Right. Okay, then shall we move to our lesson? So if I then explain that quiz number 2 paper, it's a kind of revision, we can say like that. Let's move to now our lesson. What is our lesson? Our lesson is effective nuclear charge. We are under the trends shown by S&P block elements across the period and down the group. Under that, we were actually, I explained the first one, effective nuclear charge. Effective nuclear charge. I explained what effective nuclear charge, and I explained 3 factors affecting effective nuclear charge. Do you remember the 3 factors I gave you? Can I have these 3 factors in the chat box? Yes, can I have the factors? Yes, I got 1 factor, nuclear charge. Another one? Cool, come on. Just type. Screening effect, yes. Screening effect, okay. One more, distance, yes, good. We had 3 factors affecting effective nuclear charge. What is it? One thing is the nuclear charge or the attraction. Simply nuclear charge, let's say nuclear charge. That's simply number of proton plus 1, then proton increases plus increases. When the nuclear charge increases, I explained effective nuclear charge also increases. More positive charge in the nucleus, then electron will be strongly attracted. Second thing is the distance. I think I discussed. Yes, distance between the nucleus and outer electron. When the electron goes away, far away from the nucleus, weak attraction will be there. So effective nuclear charge decreases with the distance. Next, third one I gave you, the screening effect. Screening effect, or I gave you another word for this. What is it? Screening effect or shielding effect. The more the nucleus is shielded or screened by the inner electrons, then the weaker the effective nuclear attraction. That means effective nuclear charge increases, screening effect increases, effective nuclear charge decreases. We discussed that one very in detail, and all of you understood those points. And I gave you the recording also to go through the recording and then study about this well and come to the today class. I show then, yes, you maybe you have watched it, ne? Yes, there were actually more than, views more than I expected. Maybe then you viewed it 2 or 3 times, maybe like that. Ne? These are the factors we have. Right now, look at this. I told you our main target is to understand the variation of this property across the period from left to right and down the group from top to bottom. That's the main target here. Okay, then I go from here to here across the period. I try to then compare the effective nuclear charge. When you go from left to right in a period, what about the nuclear charge? What about the nuclear charge when you go from left to right? That will increase or decrease? Nuclear charge? You know that one? Here, you know, I take lithium. I took lithium that day. Lithium atomic number 3. Because of 3, what's the nuclear charge? Plus 3. Because of 3, nuclear charge plus 3. The unit nuclear charge. Next member, beryllium. Beryllium atomic number 4. Since atomic number 4, what is the nuclear charge? Plus 4. Because there are 4 protons, then unit charge of the nucleus should be plus 4. Plus 3 plus 4. What happened to nuclear charge? Increases. Across the period, remember, number of protons then increasing Because of that, nuclear charge increases. Since nuclear charge increases, you see, effective nuclear charge should increase. Okay, according to the first point, effective nuclear charge should increase going along the period. Second thing, distance. You don't know then distance so far, but remember, when you go from lithium to beryllium, the size of electron cloud decreases. In the next property, I will explain that one. So size of the distance decreases mean effective nuclear charge again should increase. If you don't get it, it's okay. Forget about distance. We'll come to that later as the second thing. Then what about the screening effect? Lithium 3 mean it's 2 and 1. Here beryllium 2 and 2. That is according to O-level knowledge. A-level 1s2, 2s1. This is 1s2, 2s2. A-level. Inner electrons 2 here, outer electron 1. Here inner electrons 2 here, outer electron 2. What about the shielding effect? Shielding effect is always due to what? Inner electron, not the outer electron. Although you add one more electron to outer electron, it's okay. Because electron in outer energy level does not change the screening effect. Because this cannot screen this nucleus to the electron in the same energy level, same distance. So inner energy level, you get 2 electrons. Here also you get 2 electrons. So screening effect here actually remains constant. This is constant. Then we can forget about that factor. And here also we can forget about that factor. Because of this, you can say if nuclear charge increases, therefore effective nuclear charge increases. So remember that one. Going along the period or across the period, effective nuclear charge increases. Why? Nuclear charge increases while the screening effect remains constant. Nuclear charge increases, but screening effect remains constant. So because of that, true nuclear attraction felt by the outer electron here should increase. Should increase. Okay. Actually, there is a easy method to get it. Here, so far, I explained the detailed method. I mean, the logical part of this one. But I can't remember whether I gave that one last week. There is very easy method, easy question is there to, equation is there to find out effective nuclear charge. So is this one, effective nuclear charge is equal to Z minus S. That's the equation. So what is Z? Z is the nuclear charge. Nuclear charge means this whether +3 or +4. That's Z. S is the screening effect or shielding effect. That means the number of electrons in the inner energy level is actually S. Right? When you apply this one to lithium, what do we get? Z mean I told you nuclear attraction. There are 3 proton in nucleus, so nuclear attraction will be +3. Minus, you get the screening effect. Screening effect is all because of these 2 electrons, inner energy level electron only. Then lithium has +1 nuclear effective nuclear charge. So this electron has +1 effective nuclear charge. We can assume that's the true nuclear attraction felt by this electron. Then apply that equation to a beryllium. What do we get? Z is the atomic nuclear charge. That means atomic number 4 protons. Therefore, you get +4 nuclear charge. Then the screening effect. Here I told you screening effect is because of this electrons in the inner energy level only, right? So those electrons can screen the nucleus. So therefore it's still 2. Nuclear charge increases, but screening effect remains constant. So what's the value? +4 minus 2, it's +2. So this electron, the nuclear attraction is +2. Effective nuclear charge is +2. So what has happened to this? Effective nuclear charge increases going along a period. Understood? So then I explain you both ways, the easy way and the logical way, both ways. This part actually we got the note, the factors and everything we got the note. but this part we did not get it. Okay, let's have the note for that one. Right, maybe you got it. According to this equation here, +1 nuclear attraction, I mean effective nuclear charge. Here +2 effective nuclear charge. Then if I ask you to calculate the effective nuclear charge for this electron, what will be that? If I ask you to calculate the effective nuclear charge of this electron, what will be that? Again, we get the nuclear attraction +2. Then we take the inner electrons, that means shielding effect. Still it is 2. Then +4 minus 2, it's +2. Nuclear attraction +4. Effective here shielding effect 2. Then +4 minus 2, it will be still +2. So for this electron again, it's +2. Right? So true nuclear attraction felt by these two electrons now are equal. And that is stronger than this one. So this means this electron weak attraction is there. This electron is weakly bound to the nucleus. But these electrons are then strongly bound. This electron, those are strongly bound. Did you understand that? This electron is weakly bound, but these two electrons are strongly bound. When you go to the other member, boron, 3 electrons are there in the outer energy level, but those electrons are then very strongly attracted by the nucleus. So going along the period, then that attraction will be even strong. It increases. Effective nuclear charge increases. The attraction between the nucleus and electron cloud, simply outer electron cloud, then increases. Right, you got these two. If you want, you can show these things also, then it will be more clear. Here weak attraction between the nucleus and outer electron. Here strong attraction compared to this. Okay, that's you all of you understood it. Is there anyone who did not get that point? Just tell me, I can then explain it again. Is there anyone who want you me to repeat it? No reply. That means you got it. Good. Then across a period, everyone understood. Across a period, it increases. Then down the group, I repeat it again and again. Why? Because this factor, understanding this factor is important, because then you can build up the other factors based on this factor. So if you get this, you can get the other factors easily, right? Then going down the group, I take the other member in the same group. Group 1, lithium. After lithium, we have sodium. I take sodium here. You know, atomic number 11. That's 2. 11 mean it's 2, 8, and 1. 3 energy levels are there. Configuration, if you write it, 1s2, 2s2, 2p6, 3s1. That's a configuration. So since 11 proton, there will be nuclear attraction plus 11. Can you see it? Yes, you can see it. Plus 11. First energy level, there are 2 electrons. Second energy level, there are 8 electrons. Second energy level, something like this. There are 8. I can start with this. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 electrons. Okay, this is not the way. I mean, there is whole sphere. It's whole sphere, but I just got one part only. Then we have third energy level. Third energy level, you have 1 electron. Then you are asked to find out effective nuclear charge of this electron. Can you calculate and give me the value? Using this equation, you can calculate it. Can you give me the effective nuclear charge of this electron? Just calculate it quickly. Okay, I can see the answers. So what about the others? Just oh, I need more. Right. Can I have 2 more answers? Yes, it's +1. Yes, you are correct. We just apply that equation. So what do we get here? Z is actually plus 11. Nuclear attraction for sodium, it's plus 11, you know, minus a screening effect. Screening effect is what? Is that 2 only? No. Screening effect, I told you, it's the number of electrons available in the inner energy level. Now I consider this electron. That means third energy level. Before third energy level, you have second energy level and first energy level. So the electrons available in both first and second energy levels are inner electrons. Then I counted 2 here and 8 here. Total is 10. Total is 10. Shielding effect here is 10. Not just 2 plus this 8, 10. So what is that value? Plus 1. So this electron has effective nuclear charge plus 1. Then what is your idea? Effective nuclear charge going down the group increases, decreases, or remains constant? What do you think here? You know, effective nuclear charge is true nuclear attraction felt by the outer electron. That's the case, right? When you use this equation, here you get plus 1, here also plus 1. According to that, it remains constant, but it is not. If you say it's constant, it's wrong. Then what's the purpose of using this one? So remember that one. We use this equation for convenience to compare the effective nuclear charges. This equation does not give the correct value, correct idea about the effective nuclear charge. Okay, so it gives a number, but using a number, you can't express effective nuclear charge. Right. So here also then, how this electron feels the nuclear attraction cannot be accurately given by number. Here the problem is this, you know, when you consider the distance between the nucleus and outer electron, here what happened to that distance? Here this much distance, because it's from a nucleus to second energy level. But here this much distance. That's from nucleus to third energy level, far away. When the distance between the nucleus and electron increases, you know what happened to effective nuclear charge? Distance increases. Distance increases mean effective nuclear charge decreases. Remember that one. From top to bottom in a group, effective nuclear charge should decrease. What's the main reason? You know, nuclear attraction increases, but shielding effect also increases. You see this one? Nuclear attraction increases. Nuclear attraction here increases, but shielding effect also increases. So because of that, using these two variations, we can't get some idea about the effective nuclear charge variation. That's why we need nuclear attraction, shielding effect. That's why we need the other factor, distance. So according to the distance increases, so effective nuclear charge decreases. Remember that one. In that case, if this is weak attraction, what about this attraction? That will be very weak attraction. You can't say it. Here you have very weak attraction. Very weak attraction is there. The attraction between sodium nucleus and outer electron is very weak compared to the attraction between lithium and outer electron. Right. I hope now we got that idea very clear. Okay, let's have a note for that one. But before that, it's better to show these two again. Do you have enough space below lithium? Lithium, you got it actually. Do you have enough space? I don't think so. You start then not, ne? Yeah. Can you draw this one and this one roughly together and show here +1, +1? But this is weak. This is very weak. I'll give the explanation. Right. Then we got the variation of effective nuclear charge going along a period and down the group. Effective nuclear charge, you know, going along a period increases. Simply attraction between the nucleus and electron cloud increases. Going down the group, effective nuclear charge decreases. Attraction between the nucleus and electron cloud decreases. That's the variation, effective nuclear charge.